area inside one leaf of the rose. R equals 6 sine 3 theta.
Inside one leaf.
Yeah.
Okay, this was number 5.
Gosh, this is working well. Works great.
So this is going to be very similar to the one we did in class because we did one with the sine curve. And an odd number in here tells you what about this rose curve.
That's the amount of petals.
We got 3 petals. So there are 3 petals. There will be 3 equally spaced petals. So 360 divided by 3 gives you 120 degrees apart. So from tip to tip to tip, they're all 120 degrees apart. So really all we have to do is find the tip, and then we can figure out where it begins that movement and where it closes up. So the tip is going to occur when the sine function itself takes on a value of 1. So I need to know where the sine of 3 theta is 1. That'll tell me where the tip, and let's just get the first petal. So I want an acute angle. Well, typically the sine of pi halves is 1. So I'm going to take the stuff under my hand and set it equal to pi halves and solve for theta. So 3 theta has to be pi over 2. So if I divide by 3, then theta is pi over 6. So the first petal is at pi over 6. 120 degrees corresponds to, what is that? 2 pi thirds. So if you want to figure out what the tips of the other petals are, just add 2 pi thirds to that. So the second petal is pi over 6 plus 2 pi over 3,
Which is 4 pi 6.
so it's at 5 pi 6. And then your third petal, take 5 pi 6 plus the 2 pi thirds. That's at 9 pi 6, which is 3 pi halves. So here's the picture. This will be at pi over 6 right here. And then the other one's at 5 pi over 6 here. And then at 3 pi halves. So it's going to do something like that. Then come down here. And then go out there. Ooh, baby. Kind of like that. We want 1 petal, and I'll just work on the one here in quadrant number 1. And we need to figure out where it begins its loop and then what angle it closes up.
So I need to find consecutive zeros of the sine of 3 theta.
So the petal closes when the sine of 3 theta is going to be 0. So consecutive zeros of the sine function, if you think about in the xy plane or in a unit circle, consecutive zeros occur at an angle of 0 and at an angle of pi. So we need 3 theta to be 0 and 3 theta to be pi. So for the rose curve here, when I solve for theta, we get theta is 0 and theta is pi over 3. So those will be my limits of integration. Theta is 0 to theta is pi over 3 to get that first petal.
Is all that part okay with you? So this was just kind of extra.
I just did that show up.
So we've write down the formula that finds the area of the polar curve. Area has that 1/2 out here, then the integral of whatever that r as a function of theta is, squared d theta. R of theta is 6 sine of 3 theta. And then I said when it read by between the consecutive zeros of 0 to pi over 3. Okay with you? Now we'll square it. When I square the 6, I get 9. I'll pull it out here with the 1/2.
Should get 30.
Oops, that was close. 6 squared is 9. That was bad. So I take that 36 out there. Now I'm going to integrate sine squared of 3 theta. Right, square the trig function and not the angle. But to integrate this, we're going to use our formula. Before we use the formula, let's do a u du substitution. U is 3 theta, so du is going to be a 3d theta. Which means I'm going to get another factor of 1/3 out there with that number. That number is 18. So now I'm going to divide that by 3. Then we're going to integrate sine squared of u du. Yeah, I should make it a little bit bigger. Bottom line. Okay, now the integral of sine squared of u looks like, remember the formula? In
Theta.
terms of u, give it to me in terms of u.
U over 2 minus sine of u over 2.
Sine of 2u over 4. U over 2 minus the sine of 2u over 4. So 3 goes into 18 6 times. Then our formula, u over 2 minus the sine of 2u over 4. And each u is 3 theta. So this looks like 3 theta divided by 2 minus the sine of 6 theta over 4. From 0 to pi thirds. Right, we already know what happens when theta is 0. We get nothing out of that limit. So when we put pi thirds in there, we have 3 times pi thirds over 2. 6 times pi thirds is a 2 pi.
0.
Will give us 0. So the 3's cancel here and I get pi halves times 6 is 3 pi for 1 half. 3 pi square units of area for 1 pound. Okay. That kind of thing. The important thing outside of the integral is being able to find your limits on the integral. For sines, for cosines, consecutive zeros occur at pi halves and 3 pi halves. Yes. All right, then I'm ready to do some work, Lengthen. Rectangular coordinates first. So let's draw a graph of a continuous function in the XY plane. This is section 6.4. picture I want to draw is going to look something like this. Draw some sort of continuous function. Y is equal to f of x. And let's say we're going to start here with the ordered pair A, f of A. And go over here to B, f of B. And we want to know how long this curve is. If you were to get out and drive a little tiny miniature car here, how many units would you put on that odometer after you've traveled from point A, f of A to point B, f of B? We wish. The curve. And let us get continuous function from x is equal to A to x is equal to B. And the hint was on Friday. Let me squish that over a little bit. The hint on Friday was that in calculus, we cut things up into little pieces. So what the heck, we're in calculus, let's start cutting this curve up into little pieces. Let's subdivide the interval from A to B into subintervals of equal width. So this is the x-axis down here. And that's x is equal to A, and that's x is equal to B. We're going to make little tiny subintervals. And then go up there and plot those points. Each of those subintervals are delta x units long. So we partition the interval from A to B into tiny subintervals. Go and find those points on the curve. Blah, blah, blah. Oops, I also got longer on me. I skipped one. And I'm running my notebook.
It's close enough.
That's close enough. So each of those are, say, delta x units apart. And we're going to go out here to the kth subinterval. Let's say the kth subinterval is right here. So this point corresponds to xk. This is xk plus 1. And so that's this point to that point. And it's a little bitty curve there. We're going to connect it with a straight line segment that best mimics that curve, especially if those points are real close together. You can't tell the difference between the straight line segment and the curved segment. So in reality, it might look like this, but what we're doing is connecting it with a straight line. Because we can find the distance between 2 points on a straight line using the distance formula. That would be the hypotenuse of that triangle there. So let's call this distance dk, distance in the kth subinterval. So dk is going to be the square root of, I know what dk squared is, so I don't have to put the square root in there. No, I'll just do that. The square root of, yeah, I am going to do square. I'm going to do square. I don't want to write the square root each time. Got the square root sign. All right, so let's call the width of that triangle delta xk, and the height of that triangle delta yk. So by the Pythagorean theorem, the hypotenuse squared is equal to the length squared plus the length squared. Delta xk all squared plus delta yk all squared. And we're gonna add up those squared distances all the way across this length here. Well, maybe I do need the square root sign. I'll just do it here. Yep, I'm gonna put square root sign on in a minute. What I'm going to do to this expression is I'm going to factor out the delta x term. I'm going to factor out delta xk squared. And when I do that, that leaves me a 1 here, and that leaves me delta yk over delta xk squared there. You agree that if you multiply that out, you get this statement about it? So now this guy is the square root of all of that. And this is here. And so I've got product. I can take the square root of the product. This is not a perfect square, but this is, so that's going to come out as just a delta xk to the first power. Then we're going to make a Riemann sum. We've got a bunch of these little distances that were added together. So we make a Riemann sum. We get the total arc length. I should have used an S. Because arc length is usually given by S. So I'll just call it S now. It's a lowercase s. Later on when we talk about surface area, we'll use a capital S. So the lowercase s is arc length. And it's going to be the sum of all of those pieces. And then we're going to take a limit as as n goes to infinity. And what power is from k is equal to 1 to n. And then I'm going to appeal to your down to this line. What's the mean value theorem for continuous functions say? Uh-oh, it never said uh-oh. Do you recognize change in y over change in x? It's slope between two distinct points on a continuous curve. The mean value theorem says that every continuous function has an instantaneous rate of change equal to the average rate of change. What's the instantaneous rate of change given by?
Y over delta, or the limit.
Delta. So the limit of the average rate of change becomes the instantaneous rate of change that we know and love as the derivative. The mean value theorem says that in a small delta k interval, as that delta k goes to 0, as n goes to infinity, the delta k's do indeed go to 0. The delta x k's go to 0. And the mean value theorem says there is some special x, we'll call it xk star, at which average rate of change is equal to the instantaneous rate of change. So that little piece becomes is equal to the limit as n goes to infinity, delta xk goes to 0, sum from k is equal to 1 to n, square root of 1 plus, well, that becomes the derivative of this function at that special x. So I'm going to call it f of xk star squared times delta x. It'll be a delta xk, but we're going to make them all the same length. And you've seen time and time again how these Riemann sums give you the definite integral. But the definite integral is going to have an integrand that looks like a square root of 1 plus the function squared integrated with respect to x. So from x is equal to a to x is equal to b, square root of 1 plus f prime at x squared dx. So I go through the derivation to help you remember the formula. Formula comes from the Pythagorean theorem, so we have a plus sign in here. The 1 came from factoring out the delta x, so that I had a delta y over delta x. And then the limit made that thing into the derivative. So the things to remember are the plus sign, the derivative term is square, under the radical because the distance formula, and the dx. And that's the length of the curve in rectangular coordinates. When you're in calculus 3, you're going to write functions, maybe vector value functions, maybe functions of several variables as functions of the arc plane. So we can write things now in terms of polar coordinates. Well, maybe polar coordinates don't suit you, and you can write things in terms of length of an arc. So this will show up again for you in Cal 3. But let me point out that we're integrating something that has a square root sign and something squared inside of it, but it's a sum. So automatically it spits out a bunch of things that we don't know how to integrate. Take one of the simplest rectangular curves, take a parabola, and let's compute the arc length along the parabola. Y is equal to x squared from, say, x is 0 to x is 4. And we get an integral that right now we don't know how to do. But let's set it up. Use that formula and set up the integral to find the length of y is equal to x squared from x is 0 to x is 4. Picture without the stalling. Turn around and think. 0, 0, x is 4, y is 16. Help you remember the formula, I'll write it down again. S is the integral from a to b, square root 1 plus f prime squared dx. The derivative of x squared is just 2x. So I'm going to put the 2x right here. So I'm going to integrate from 0 to 4, square root 1 plus 2x all squared. But when I go any further, I gotta know whether or not you know that you don't know how to do that integral. Do you know that you don't know how to do that integral? Firstly, you can't take the square root of each term, otherwise I'd have done it way up here. right? Can't take the square root of each term in a sum, only in a product. I can't integrate a second degree polynomial as the inside of a function unless its derivative appears outside the rule. With a u du substitution, boom, I can do that. But if I take u to be 1 plus 4x squared, du is 8x dx. And because I don't have an x out here, I can't do that integral. Agree? Well, I lied. I can do this integral.
Oh, yeah.
In chapter 7, you'll be able to do this integral. We have different substitutions that we can make. But right now, with calculus 1 techniques, you don't know how to do this integral. Okay. So the problems in this section are contrived in such a way that the functions we start with are pretty funky, but they have derivatives that after you square them, either gives you an entity under here that would be a u du integral, or gives you an entity under here that is a perfect square. And so you can take the square root of a perfect square, right? So the problems in this section are very much contrived in that way. And my examples will be as well. So my first example is, let's just take a line segment. Y is equal to 9 minus 3x. And let's find the length of that line segment from x is 1 to x is 3. We'll do it with the distance formula, and we'll do it with our brand new never been used calculus formula. Find the length along y is equal to 9 minus 3x from x is equal to 1 to x is equal to 3. And first degree functions, just the line segment. So we don't need any fancy calculus. Let's just get the two endpoints of this line segment. When x is 1, y is 6. So 1, 6, I'll put right here. And now when x is 3, oh, let's put 1, 6 up a lot higher then. Let's put 1, 6 right here. Because when x is 3, y is 0. Oh, move it over. So just use the distance formula first. Right. The distance formula for the Pythagorean theorem. That length s is the square root difference in the x's, so 3 minus 1 squared, plus the difference in the y's, 0 minus 6 squared. So 2 squared is 4. 6 squared is 36. The length of that curve is the square root of 40. Good?
Yeah.
Yawn. Now let's use the formula. S is equal to the integral of the square root of 1 plus the derivative of that function squared, integrated with respect to x. So I'm ready to write. I'm going to integrate all my x's from x is 1 to x is 3. What's the derivative of that function? Negative 3. So my integrand's constant. It's the square root of 10. So I'm integrating the square root of 10. Then I just get the constant times x. And when I put the 3 and the 1 in there, I'm going to get 3 minus 1. 3 minus 1 is 2, so I get 2 times the square root of 10. Can you rewrite the square root of 40 as 2 times the square root of 10?
Yeah.
Because we've got a common perfect square of 4 times 10 in there. Square root of 4 is 2. Right, so it does indeed work for straight lines. It's going to work for any vector. Okay, next. Do that one. Looks like fun. Let's do it. What does that have to do with witchcraft?
Teach us the technique.
Let's integrate or set up the integral that finds the length. Find the length of the arc of f of x is equal to the natural log of the cosine of x on the interval from 0 to pi over 4. So on 0 to pi over 4, the cosine of x is never 0. So the logarithm is well defined. It's a continuous function. It should just look like a log function. We'll need the derivative of that. Can somebody take the derivative of that function?
1 over cosine of x times negative sine x.
Whatever cosine times negative sine, which gives us a negative tangent. Sine over cosine is a tangent. Okay. Now in our integral, that is square added to 1, take the square root out. So our problem is going to look like the integral from 0 to pi over 4, square root 1 plus a negative tangent of x squared dx. So far, so good? Okay, so we got the square root of, after you square that thing, the minus sign is gone, but you get a tangent squared. So I don't have a u du integral. U is equal to 1 plus the tangent squared. And du is 2 times the tangent of x times the secant squared of x. So I don't have that outside. So it's not a u du integral. I need somebody to help me out. Concentrate, huh? Everybody, his dog knows that sine squared plus cosine squared is 1, and if your dog doesn't know that, you got some teaching to do.
My dog is dead.
Everyone knows sine squared plus cosine squared is 1. So if I take that 1 and divide every term by cosine squared, we have a Pythagorean identity for tangent squared. Tangent squared plus 1 is equal to 1 over cosine squared, which trig function is 1 over cosine squared. Ask your dog. Secant squared. You can leave the Ouija board out there. Fido, can you hear me? So that's a perfect square under there. 1 plus tangent squared is equal to secant squared. right? Now that I got a single term under there that's squared, I can take the square root of it, and I get that I have to integrate a secant of theta. Or secant of x, sorry. Do you know a trig function whose derivative is just secant of x? What is the derivative of secant? Derivative of secant is L1. Derivative of the secant of x. Secant x tangent x. So I don't have secant x tangent x. Then we saw that the derivative of tangent was secant squared. So I'm going to show you how to do this by taking that integrand and multiplying it by 1. I'm going to multiply it by the secant of x plus the tangent of x over secant of x plus the tangent of x. That's the little bit of witchcraft I talked about. We'll just call it a standard trig. Your dog won't know this one.
Okay. Great diet.
Because look what happens if I multiply that out on top of the bottom. I get this integral. It's secant squared plus secant tangent. On the bottom, I get the secant of x plus the tangent of x. Have you noticed anything helpful about that expression? Speaking of helpful, you're not. What's the derivative of tangent?
Secant squared.
What's the derivative of secant?
Secant x.
The sum of the two terms in the bottom have as its derivative the top.
Oh,
We have a UDU integral.
yeah.
U
Nice.
to be the bottom and DU is going to be the top. If U to be secant of x plus tangent of x, then DU is secant x tan x plus secant squared of x dx. It doesn't matter the order, addition is commutative, but that's the numerator. So that gives us a 1 over u du integral. Can everybody see that? There's a similar trick for integrating cosecant. So now we're integrating 1 over u du. What do you get when you integrate 1 over u?
No, I don't.
There we go. We'll put it in absolute value bars, where u is the secant of x plus the tangent of x. So I get the natural log of secant of x plus the tangent of x evaluated from 0 to pi over 4. So we're going to get the secant of pi over 4. That's 1 over the cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. So secant of pi over 4 is 2 over the square root of 2. Tangent of pi over 4 is the sine over the cosine, each at pi over 4. Both of those are square root of 2 over 2. So I just get 1 out of that. Now I'm going to plug a 0 in there. Secant of 0 is 1 over the cosine of 0. Cosine of 0 is 1. So secant is 1 over 1. Tangent of 0 is the sine of 0 over cosine of 0. Tangent of 0 is 0. So what's the natural log of 1? Natural log of 1 is also 0. 2 over the square root of 2 to rationalize it. over the top and going by the square root of 2? It's just root 2. So our arc length is the natural log of the square root of 2 plus 1. When we get to chapter 7, you'll see this over and over and over. So you'll learn it. You'll learn that the integral of the secant is the natural log of the secant plus the tangent. It's going to be one that we add to our list of formulas. Okay. So even though it had that little thing in there, it still was tried to stuff under the radical sign was a perfect square. Let's do one more. You'll see what I mean here. About three. Let's find the arc length along graph. 12xy is equal to 4y to the 4th plus 3 from point A, whose coordinates are 7/12, 1, to A, coordinates of 67 over 24 to 2.
How do you come up with problems like this?
I opened the book and I looked at the problem and said, that looks like a good one.
How did they come up with problems like this? They have some like magic computer that just spits out.
Yeah, yes. I mean, you can do it in terms of letters and then figure out numbers that be nice whole numbers to go there.
Well, the X like comes out clean almost, isn't it? Because like there's a 12 and like a 7 over 12. And like,
Say it again. Say it again, Chase.
Like the fractions kind of almost go away anyway.
The 12's gonna cancel the 12.
Well, yeah, well, if you plug this ordered pair in.
Oh, you
this
get
in
one.
there,
never mind.
and that one in here, that'll equal the same thing. Same deal here. This satisfies the equation. But one thing I want to point out is that our arc length integral as a function of x would have us integrating from 7/12 to 67 over 24. Not two of my favorite numbers. And then I would have to write y as a function of x. Can you take this equation, excuse me, and write y as a function of x? I got a y to the 4th and a y to the 1st power. Is there any kind of algebraic manipulations allows you to get y all by itself and a function of x on the other side? It's not possible. When we had stuff like this, and we had to take the derivative out, we used implicit differentiation. We didn't have to work that hard. The derivation that we did with the distance formula works just as well as if I factored out a delta y squared. And then I'd have a delta x squared over a delta y squared, and that gives me an x prime term. There's nothing magical about doing this as a function of x. We can do this as a function of y. We can write our arc length formula as s is equal to the integral from y is equal to some number to y is equal to another number of the square root of 1 plus, in here you would have x prime, where x is a function of y, squared dy. You don't have to get y, f of x, which is the y, by itself. And that's the point of this problem. Then I can integrate from 1 to 2. And I only have this x here, so it's easy to write x as a function of y. Just divide both sides by 12y. take the derivative of that, and I don't really want to do the quotient rule. So I'm going to simplify that a little bit. I'm going to break that up. That's a single term in the denominator. So I can just put that denominator underneath each of the terms in the numerator and write x is equal to 4y to the 4th over 12y plus 3 over 12y. And when I simplify, 1 of the y's cancel here. 4 goes into 12 3 times. So I could write that as 1/3 y cubed plus 1/4 y to the negative 1. See how I did that? I wrote it like that because I need in my integrand the derivative of that all squared. And now I can just take the derivative of that term by term. Okay, so we're going to do things as a function of y. So x prime, bring the 3 down, it cancels with the 1/3, and I get y squared. Next term, bring the negative 1 down, I get a negative 1/4, y to the negative 2. Let's put that right here. And then I'll have to square it. And we can integrate from y is equal to 1 to y is equal to 2. One plus x prime y squared minus 1/4 y to the negative 1 squared dy. Can't integrate the way it says. We'll have to spread out that term. Let's take the y squared minus 1/4 y to the negative 1 and square it. So I want you to do it first. I want you to notice what you get when you square that thing. FOIL it out. Y squared minus 1/4 y to the negative 1 times y squared minus 1/4 y to the negative 1. It simplifies. Let me know what it simplifies to.
Okay, y to the 4 minus 8 plus 16 over y to the 4th, and then the plus 1.
Let's see how you did that.
Oh wait, never mind. I accidentally had the 4 and the.
Oh, this is a 2. I wrote that down wrong.
Okay.
Help me out here. This is a 2. Right? I need this here minus 1/4 y to the negative 2.
Never mind.
That helps that I got the negative 2 there. Because somewhere in there, you're going to multiply a y squared with a y to the negative 2, aren't you? What is y squared times y to the negative 2? It's just 1. It gives you y to the 0, which is 1.
Would it just be like y to the 4 minus like 1/2 plus 1/16 times y to the negative 4?
That's exactly right. Here's what you get if you square it. 1 plus, you're going to get a y to the 4. You get 2 times this product. But the 2 y's multiply together to give you a 1. 2 times 1/4 is a half. And I'm going to get negative 1/2 in the middle. And then we get the last term squared plus 1/16. Raise the power to the power by multiplying exponents. So I get y to the negative 4. So if you were multiplying that out, did you get to that point? And what I can do is I can take this one and subtract the 1/2 and just rewrite that with a plus 1/2 in the middle. Y to the 4th plus 1/2 plus 1/16 y to the negative 4. By joining that term with that one. If you look at that hard enough, get your good eye. Look at that hard enough, you might recognize that that is a perfect square. What? Looks almost like what I got here, except for the middle term has a different sign, right? So instead of having an a minus b all squared, it should have an a plus b all squared. Instead of having a minus sign here, it should have a plus sign there, and it should give me that. Do you notice that? The factor gradually multiply that out. Tell me if I'm lying to you here. That's the same thing we multiplied out right here, except I got a plus sign. So the only thing that should change is the sign of the middle term. So I should get that with a plus sign here. And that's what we got right above it. So even though you didn't think of doing that, I told you the problems in this section are tried. That should happen if you did your squaring right and you're adding right terms right. You should get something that's not perfect square. Just look at what it is that was squared to get you that. Okay, try to factor when you get at this point. To get a y to the fourth, I need y squared times y squared. To get a 1 over 16, I need 1/4 times 1/4. To get a y to the negative 4, you need a y to the negative 2. To get the plus sign in the middle, you need a plus sign there. But that allows me now to take the square root of a perfect square. But I'm left to integrate that stuff in the parentheses. Right, so let's go ahead and do the integral. I won't do the number crunching. I'll do the integral. I get y cubed over 3. Add 1 there, gives me negative 1/4 y to the negative 1. Evaluated from 1 to 2. Do all the numbers. You should get something in the neighborhood of 59 over 24.
Nice clean number.
Okay. Sometimes you might want to change the variable of integration to a y. Sometimes it'll work either way. But what you should get is either something that's a perfect square or something that can be manipulated to a u/du integral. Now let's talk about polar coordinates. What are our conversion factors for x and y in polar coordinates? X is equal to r cosine theta, y is equal to r sine theta. So I'm going to go back to the step in the derivation of the formula that looked like this. The delta x squared plus delta y squared is our distance squared. We go back to that step. Let's see if I remember how to do this. You guys can't let me get stuck because I didn't look this part over. I'm going to do it from memory. We said x is r cosine theta, and y is r sine theta. And so, if I think about the change in x and the change in y now, where x and y are functions of theta, I'm going to use these things as functions of theta. So I'm going to divide everything by delta theta squared. But dividing by delta theta squared has to be compensated for, so I'm going to take that and multiply now by delta theta squared. So I've multiplied by 1. Each of those delta theta squareds would cancel. Then that last one is a perfect square in a product. I can take it out of the square root sign. That's just be delta S, not square. And that's gonna come out like that. So our integrand is gonna have this stuff in it. We're gonna have integrals with respect to theta when we make the Riemann sum. But what I'm gonna do now is go over here and treat these as derivatives. Take the derivative of x with respect to theta, take the derivative of y with respect to theta, and sub those in. But x is a function of r and theta, while r itself is a function of theta. R is not a variable, R is a function. So when I find my derivative of x with respect to theta, I'm going to use the product rule, where R is an implicit function of theta. So I've got the first times the derivative of the second. Here the cosine is minus the sine of theta, plus the second times the derivative of the first. So then I'm going to get a delta R, delta theta. I'm getting an R prime term.
What did you just do there?
That's implicit differentiation. So that's like when you always had to tack on the y prime in implicit differentiation, you get an R prime here. And if you want, I can use a prime instead of the delta R over the delta theta. And that might be easier. So we'll get minus, let me put it in the other order. We'll get R prime cosine theta minus R sine theta. And let's do it again. So delta y over delta theta, just using the implicit derivative. First times the derivative of the second plus the second times the derivative of the first, which is going to give us an R prime. And what we have to do is put that first line in here and square it, and put that second line in here and square it. So it's going to look pretty long. The delta x over delta theta was R prime cosine theta minus R sine theta. Then I got to square it. Plus, the next line is R cosine theta plus R prime sine theta. And then I got to square that. And this thing out here eventually will turn into a d theta. Now let me square this one, square that binomial. First term squared, twice that product, plus the last term squared. Here goes the squaring. First term squared, R prime cosine theta squared. 2 times this product, so I'm going to have a minus 2 R prime R cosine theta sine theta. Plus the last term squared to be an R squared sine squared theta. Now I'm going to add to it this guy squared. And I'm just going to put it underneath because I've run out of room to go that way. So I get plus R squared. Let me say R cosine. Let me say R squared cosine squared theta. Then I'll take 2 of these, so plus 2 R prime R cosine theta sine theta. Plus the last term squared, R prime sine theta squared. And all of that is under one great big square root sign. And it's going to take by the delta theta, but I'm going to blow that off for a while.
A big equation.
It's going to get smaller. Got the red. It's that one. And that one. What about those 2 that I underlined there? They add each other out, don't they? One's positive, one's negative, those are gone. Okay. Next, I have a couple of r squared terms. I have an r squared sine squared added to an r squared cosine squared. So I've got r squared sine squared theta plus r squared cosine squared theta. That's this one, that one. This is an r prime squared cosine squared plus r prime squared sine squared. Okay, from these two, I'm going to factor out the common factor of r squared. And that leaves me with sine squared plus cosine squared as the other factor. Plus, from these two, I've got a common factor of r prime squared that I'm going to pull out. And my other factor then is cosine squared plus sine squared. So here's where you're done. It comes in handy.
Oh, yeah.
What is cosine squared plus sine squared plus cosine squared? Both of those are one. So this part right here in the formula, see, I lost that a long time ago, but it's right around. That part right here that's going to be in the Riemann sum will look like an r squared plus an r prime squared. So the moral of the story is that the arc length formula in polar coordinates has that as your integrand with respect to theta. So in polar coordinates for r is some function of theta. Arc length looks like an integral from theta is equal to a to theta is equal to b. This goes inside here. R squared plus r prime squared d theta. It doesn't have a one plus derivative squared like rectangular coordinates did. It has an r squared in there. And everybody's going to forget that at one time or another. Whether it's doing your web work or doing your test, you're going to forget the r squared. You're going to put one there and you're going to get stuck. Not very many points, partial credit. The polar coordinate formula is different than the rectangular coordinate formula because of the change of variable. Again, for our problems, even the simplest ones, this formula is going to be too hard to use. But let's use it on one that we can do anyway. Let's, where's my example? One that we can do without the formula, one that we can do with. What kind of graph is r is equal to 5 cosine theta? It's a circle, right? It's a circle of diameter 5. This is the entire length around a circle of diameter 5 is going to be circle. Circumference, remember the circumference formula in terms of the diameter.
Or it'd be pi 5.
Pi times the diameter. The circumference of the circle is 5 pi. Well, I don't want the circumference, I just want a piece of the arc. Let's find the piece of the arc, find its length from theta is equal to 0. Find the length of the arc equal to 0 to theta is equal to 3 pi over 4. Without any calculus. Here's our circle. And let's just center it on put the center here so that we can do it without having to think too hard. Here is pi over 2. Here is pi. Here's 3 pi over 4. What fraction of the circle do we have here? Well, we take 3 pi over 4 divided by the whole circle. So the pi's will cancel, that's 3/8 of the whole circle. So this should be 3/8 of the entire circumference. So that arc length is 3/8 of, what do we say the circumference was, or 5 pi? We should get as our answer 15 pi over 8. Do that right? 3 pi over 4 divided by 2 pi. Pi's will cancel. I didn't get that number. Let me think differently.
Whole circumference. Really get 3.
Where is that circle over here? Let's see where that is. When I put it up here, it looks like that. So maybe I can't do that maneuver.
Yeah, so once you get a half the,
Okay, so from 0 to pi over 2, 3 pi over 4 puts us here. Cosine of 3 pi over 4 is negative square root, so that's going to put me back to here. So it's going to give me half plus quarter. It still should be 3/8. I don't know. Forget the final fraction stuff. I'm gonna go from here to there. No, it's spitting back here. Who cares? Let's use the format too. I'll think later. Okay. What's our try?
-5 sine theta.
And then let's put it into our formula. Arc length is going to be the integral of the square root of r, which we did it right for r squared plus r prime squared. So we're going to go from 0 to 3 pi over 4. R squared is 25 cosine squared theta. R prime squared loses the minus sign, and we get 25 sine squared theta. What are your thoughts on that?
Factor out 25, set cosine squared theta plus sine squared theta equals 1. And then take the square root of 25.
Good. What do we do? Factor out the 25, the other factor out is 1. And so I just have a 25 there, square root of 25 is 5. So we're left with integrating from 0 to 3 pi over 4, 5. So we get 5 theta. To be evaluated from 0 to 3 pi over 4. And so I'm getting 15 pi over 4 minus 0. So I don't know why I get 15 pi over. They're just going to think about the symmetry of the circle over there. I don't know why I got 15 pi over 4 as opposed to 15 pi over 8 when I did it this way.
Try it again, maybe.
I'm not gonna try it again.
Do it.
I can't do it in a minute. So, it's gotta be contrived for you. If you took our cardioids, we wouldn't be able to put that into our formula, right?
Here's a cardioid. R says equal to 1 plus the cosine of theta.
Its derivative gets you minus sine of theta.
But now look at what happens when you have r squared plus r times squared. If I square that, I get 1 plus 2 cosine theta plus cosine squared theta. If I square that, I get sine squared theta.
So at best, you could write this as 2 plus 2 cosine theta, but it's going to be under a radical sign.
And you can't integrate that because your d theta doesn't have any signs in it. So even for something very simple, we can't use this formula in practice unless the original function is something kind of odd-ish.
Yeah.
So you'll see some of the equations that give you equations of spirals.
Find the arc length around the spiral.
These are the things that generate a spiral with an theta plane.
Is there a way to solve those with like more advanced techniques, or is it just like in the realm of do not solve?
Definite integrals that are ways to approximate
Right.
definite integrals. You can do it in factorization technique.
Sure. Okay. Right.
So, but in terms of indefinite integrals, there's a lot of them that you can
Fake your way through, but I don't know about that one. Bring your hard hats next time, and there's a section next time to work. You need your hard hats.
Don't think I'm to ask me, bro.